Good morning. Today we are heading into the last chapter of the semester, chapter 20. There's a lot of stuff here too. I want to thank everybody for their patience with chapter 19. A ton of stuff in chapter 19. I know we went way over. At some point we're gonna make up for that. We're gonna compensate. We've had a couple of lectures, I guess, that wrap things up early. I don't think chapter 20 is going to be one of those. Now, I think this is going to be manageable today. Let's take a look and see. Chapter 19 was listed as the first law of thermodynamics, which was energy conservation. And chapter 20 is titled the second law of thermodynamics. And this is a little more difficult to explain. It's based on the principle of entropy. So if you've heard about entropy, if you watch different science shows and or listen to some science blogs or something, or podcasts, then you are familiar more so with it. Anyway, let's get into some of the topics and see what we are getting ourselves into. Again, this is the last chapter of the semester, so this is kind of exciting. The second law, the introduction here is saying that the second law of thermodynamics is a statement about which process occur naturally and which don't. Okay, does that tell us anything? No. But here's the statement. Heat can transfer spontaneously from a higher temperature region to a lower temperature region. We go, well, yeah, and we understand that now because in the higher temperature region, the molecules have above average energy, and in the lower temperature region the molecules have below average energy, and through random transfers of energy, the energy is going to statistically even out to what we consider to be the statistically most likely distribution. And back in chapter 18 we looked at that in some detail with a collection of gas molecules. So entropy is actually based on statistics. The idea is, statistically, we would expect if I have some water at 20 Celsius and I have some water at 50 Celsius and I put them in contact with each other, the arrow's going the wrong way. Oh no, the heat arrow needs to go back the other way. That's got to get changed. Okay, so what we've got then is that the faster moving molecules are allowed to come into contact with the slower moving molecules, and statistically, on average, these start to pick up speed and those slow down. Now we call that the flow of heat, but it's really just random molecular motion, and through collisions, the energy gets kind of spread around uniformly. So we're going to say that each side of this has a mass of 100 grams. Now, surprisingly, we can calculate entropy by taking the heat that's being transferred, divide it through by the temperature when that transfer takes place, and carry out that integration, and that works. It's surprising that we can actually keep track of this approach to kind of uniform distribution of energies, most statistically likely distribution of energies, just by carrying out this integration. Now the dq in here is going to be mc dt. Substitute that in. We get a delta S formula that is the mass of the sample times the specific heat of the material times the natural logarithm of the final temperature over the original temperature. Now with these two samples, let's take the one on the left. The original sample, the original temperature is 293. Now, oh, I see what happened. Sorry, I thought there were two samples. I guess I wrote this. So here is the sample. We're adding heat in, and we're taking just one sample, not two. We're taking one sample and raising its temperature. What's going to happen in terms of entropy? So the temperature starts out at 293. It tops out at 323. That is 100 grams of water with a specific heat of 4.186, and to calculate the entropy, we need the logarithm of the final over initial temperature. I carry that out, and what I get in terms of units, this is kind of interesting. As we approach this distribution, this most likely statistical distribution of energies, that comes out in units of joules per Kelvin. So that would be how many of joules have we transferred divided by the temperature at which the energy was transferred. Very interesting. It turned out to be 40.8 units of entropy, and those are joules per Kelvin. All right, for any closed system that we follow, the net entropy always is increasing. Now, in this case, it's not a closed system yet, because we're only looking at one sample. Now, we have to look and see where the heat came from to be able to do a more complete calculation. But as far as this one sample having its temperature go up, that increases the amount of entropy. So, and entropy is kind of the central feature here. Now, I think the textbook waits and introduces entropy a little bit later. I always feel like it's important to get the entropy, the basic idea out there right away. So let's try another. Here's the 2 water sample. Got ahead of myself. This is 20 Celsius. This sample is at 80. There are now 2 samples. This is 250 grams. This is 250 grams. Now I put them in thermal contact. Since the specific heat for water is roughly a constant, and we have equal sizes, what we can say is the final equilibrium temperature will be halfway between, and that would mean that both samples now are at 50 Celsius. So if I look at sample A, I wrote this and I'm using A and B, delta SA, MC logarithm, this is the final temperature, the final equilibrium, 50 Celsius, divided by TA. 250 grams, 4.186 joules, that's the specific heat. Now remember, that's got to be kelvins. It's a ratio of temperatures. All the formulas that we're looking at now, you've got to put the temperature in kelvins. And again, that's one of the things that I'm not very sympathetic about, is putting in Celsius instead of kelvins. So make sure that you're very Kelvin oriented, and you know when you're going to absolutely need to put kelvins in. So here's the final temperature for sample A, and here is the original sample. Now, calculating the entropy on sample B looks very much the same, except it started at a higher temperature and ends up lower. Now, carrying out the calculation says that the heat went into sample A, and its entropy went up. But sample B lost heat. Heat transferred away from sample B, and its entropy went down. So it's not as randomly distributed, or rather, it just doesn't have as much entropy. At lower temperatures, there are fewer options for your molecules. So in general, if you go to higher temperatures, the entropy will go up, because the molecules have more options if you've got more energy. And that means that they can reach different speeds and kinetic energies that weren't accessible to them before, and that means the distributions of all the kinetic energies represent more entropy. So sample A boosted its entropy by 102. Now when we finish, they both have the same amount of entropy and energy, but the entropy in sample A went up by 102. The entropy in sample B went down by 93. Now, why are they different? Because the heat was transferred at different temperatures. So what that says is anytime we go from 2 samples that have different temperatures and then go towards thermal equilibrium, the overall entropy, if I add the entropy increase and the entropy decrease, it's positive. So a positive number for entropy says this process is not reversible. Now, energy conservation says why? Energy conservation says that going this direction or this direction, who cares, They both represent the same amount of energy. So the first law is not enough to explain why this process goes from left to right, but it does not spontaneously go back left. Okay? It won't, once you have mixed hot and cold water, nature is not going back. The overall entropy in the universe has gone up, and you can't get back to the entropy levels you had before. So think carefully before you mix hot and cold water. Remember, the universe can't go back to the state it was in before that happened. So this is a statement from the second law saying that because the entropy went up, statistically, it's very, very, really very, extremely, very unlikely that this process could ever reverse itself just by chance. Okay. Now, statistically, there's a, you can calculate what's the probability that the molecules will rearrange themselves with all of the higher kinetic energies in one side and the lower kinetic energies on the other side. And the chances of that happening are enormously tiny. All right, now, how can we use this principle of entropy? And in this chapter, maybe the most important part, in addition to understanding entropy calculations themselves, is to look at what we call heat engines. So we operate a lot of heat engines. Heat engines consist of some kind of a combustion chamber where we're generating a bunch of molecules, some kind of molecular system that has a lot of energy, something at a really high temperature, and then we allow that high temperature region, we allow the heat to transfer away from that high temperature region and operate an automobile or a power plant. So if the power plant's running off like natural gas, I think California still produces half their energy or more from natural gas turbines. Or if it's a nuclear power plant, you generate a bunch of heat, you use that to run a turbine and generate electricity. So those heat engines, heat transfers away and ends up going into the environment. Now, along the way, some of that high temperature energy that we generated is converted into mechanical energy. So that's where the engine part of heat engine comes from. We take some of the heat that is generated and we convert it into mechanical energy, and we drive our cars and we generate electricity. So that's what heat engines are all about. Now, when we look at heat engines and refrigerators, let's look at we'll get back to refrigerators. So here is the combustion chamber. I like these diagrams drawn this different orientation. Again, it's a personal preference. So here's the high temperature region, TH, and it's transferring heat, a certain amount of energy, QH. Now, some of that energy goes into work. That's the good part. Some of it goes right into the environment. And what we find is it's impossible to get 100% conversion of the heat that we've generated. We can't get 100% of that to go into work. And we can actually use the principle of entropy, the second law of thermodynamics, to calculate under perfect conditions how high could the efficiencies be. So let's say this. Let's say we build this heat engine and we measure the high temperature region, we measure the low temperature region, which is typically the environment. We go in and measure how much heat are we generating, how much work are we getting out, how much heat goes right into the environment, and we can define an efficiency. So the efficiency of this would be work divided by QH. So the amount of energy we get out divided by the heat that we invested. Now that can be restated. The work we get out is equal to QH minus QL. Energy is conserved in this process. So that says the efficiency could also be written as 1 minus QL over QH. Now let's make up some numbers. Let's say that QH is 1,000 joules. So we're constantly generating heat let's take a 1,000 joule sample of that heat and ask how much work did we generate? Well, let's make up a number there too. Let's say it's 350 joules. So at first you might look at that and go, oh my gosh, this engine is not very efficient. We generated 1,000 joules of thermal energy, but we were only able to convert 35% into heat. Doesn't sound very good. That efficiency would be 350 divided by 1,000. That's 0.35, or 35% efficient. Now, it says that QL, in this case, would be the remaining energy. So 65% of the heat that we generate goes immediately into the environment, and that's not useful to us anymore. We can't operate a power plant, we can't run our cars, all the things we like to do with all of this energy that we're generating all the time. That's 650 joules, that's just random thermal energy now. It's just internal energy of the molecules scattered throughout the environment. Now, if we add to this diagram, let's bring in the second law of thermodynamics and calculate entropy changes. Now, every time we transfer heat away from the combustion chamber, that's a reduction of entropy. And we can write that as the heat divided through by the temperature that it transfers. So this becomes a formula. We don't have to use the integration. We're going to assume for the heat engine that the operating temperatures are constant. So we ignore the integrations, and we'll not ignore them. We use a constant temperature, and that means we can bring the temperature outside the integration, and then it just becomes QH over QT, but that's a minus sign. So the entropy here continually drops. Now we keep creating more entropy by burning more fuel, but every time we send some out, that's a drop in entropy. There's an entropy increase in the environment happening because we're transferring energy there. Now, what the second law of thermodynamics says is, statistically, I can't generate a bunch of random kinetic energy and then organize 100% of that into work. If I create a bunch of randomly moving molecules at high energy, the entropy increase when I transfer out the QL has to be at least as large as the entropy drop. So what we can do is this. We go, okay, under ideal conditions, the entropy increase of the environment has to match the entropy drop as the heat comes out of the combustion chamber. And that says delta SH plus delta SL has got to be greater than or equal to 0. And that says that QH over QT is going to be less than or equal to QL over TL. And that says that QL over QH has to be greater than or equal to TL over TH. It says that there's always going to be a minimum amount of energy that goes directly into the environment. Now, ideally, the second law says the best we could hope to do is QL over QH equals TL over TH. So when we're thinking in terms of theoretical efficiencies, what's the best we can hope to do? Instead of working directly in terms of the Q's, that formula is in terms of the temperatures. So when I look at the operating temperatures, that's going to tell me what the best efficiency could be. So let's make up some numbers there too. Let's say the combustion chamber is at 500 kelvins and the environment is at 300 kelvins. That's the QL depository. That's where the QL is going. Under ideal conditions with these operating temperatures, 1 minus TL over TH, well, that says for these temperatures, the best efficiency we could ever hope to get would be 40%. Okay. And again, it comes down to absolute temperatures. We're already in an environment at 300 Kelvin. We really can't get the environmental temperature to go much lower I mean, we're going to be building our power plants, and we're going to be operating our automobiles in this environment. So the idea is then to build combustion chambers that operate at really high temperatures. So we could do that. We could go to higher temperatures, and that would boost the theoretical efficiencies some amount. But still, we're not going to reach temperatures high enough to be able to get these efficiencies anywhere close to 100%. So this is actually pretty good. If we have a power plant that's operating at 35% efficiency, we're feeling pretty good. That's a high efficiency power plant. Now, ideally, we would move away from heat engines, and the heat engines are primarily being driven by fossil fuels, and that's putting out a lot of carbon dioxide. So in that sense, we want to move away from heat engines and replace them with things like hydroelectric, solar, voltaic energy sources, wind power. Those don't have the limitations of the heat engine efficiencies, and they're not dumping a lot of carbon dioxide into the atmosphere. Now, nuclear is also an option, and then you have to decide, do we really want to deal with nuclear waste material? Do we trust ourselves enough to say that we could generate tons and tons and tons of radioactive material and keep that safe for generations to come? And I feel like that's a bit of a risk too. We have these alternate energy sources out there. You know, I'm in favor of using the alternate, the wind, the solar, geothermal, hydroelectric. So those seem like the sources we want to convert to. Also with the automobiles that we operate, we don't want to run those off of fossil fuels either. So in that sense, the heat engines, maybe we want to move away from them. All right, now what we're going to do is we're going to take a look at a couple different heat engines. And we're going to look at heat engines that operate in a repeating cycle. Now, even though this is in a repeating cycle, many of the features that we use here will apply to something like a power plant. Now, a repeating cycle is more like an automobile engine, an internal combustion engine, where we have pistons moving back and forth. We ignite the fuel. We get a lot of high pressure. Generates the high pressure that we generate pushes mechanically on the piston, and then we reset that and we do it again, and we may be doing it many hundreds of times per minute, many thousands of times per minute actually, and so many times a second, many times a second. All right, here's a diagram of a heat engine for a steam engine. So here is a boiler. We're using the heat engine from the boiler to generate some high pressure steam. High pressure steam comes through, it's allowed to come in, push a piston, and then it's allowed to leave, and then we condense it. And then we bring the coolant, the water, back around again. And so we get these periodic pushes that provide mechanical energy. Similarly, or differently, in a turbine, we can just take the high pressure steam and run it through some kind of a propeller system and just continuously generate that mechanical energy. Okay. Here are the individual stages, the steps that take place in an internal combustion engine in a car. We're compressing the fuel-air mixture. Here's where we're bringing it in, and then we compress it. I'm not so sure about the pictures here. And then once it's compressed, we ignite it, create a really high pressure, and that pushes down very forcefully. So to get energy out, we need to push the piston down much more forcefully than what was required to compress the fuel-air mixture, and that's very easy to do with the chemical reactions using gasoline. So the energy, the efficiency, as we said, is W over QH. And it can be written, so this is kind of a repeat of those formulas. And what about car efficiency? Let's take a car efficiency. Let's say that the engine is 20% efficient. It provides 23,000 joules of mechanical work every second. That sounds like 23,000 watts would be the power of that engine. How much heat is required, how much heat is discharged each second. And so let's set up our little diagram here. Here's the car taken off. It's a 23,000 watt car. Oh no, I wrote horsepower. Cover that up. Okay, that's 31 horsepower. But more importantly, it's 23,000 watts, and the efficiency is W over QH. Now every second, what we're told is the power is referring to the work being done. So it's the work that we want out of this, and we're saying that that's at a 20% efficiency. So if that's at a 23,000 joules at a 20% efficiency, we can divide through by the efficiency, and that tells us that QH needs to be 115,000 joules. It needs to be 5 times as much. Okay, now I'm guessing these are probably representative numbers as to how efficient, a fairly efficient automobile internal combustion engine would be. So this is 100% of the energy we have to work with. 20% of it went into work, and that says the remaining 80% is going to go right into the environment as we operate these engines. So maybe by the end of today's lecture, you guys will all be committed to buying an electric car. I know they're expensive. To buying an electric car. Now, going back to how does this apply to entropy, and we've already kind of talked about this, that entropy says that when we generate a bunch of heat, it is not possible to convert that heat 100% efficiently into work. We're only going to get some fraction of that. Maybe a power plant is 30-35% efficient. Maybe an automobile engine is 20-25% efficient. So some portion always goes into the environment, usually the larger portion, and the ideal efficiency will depend on operating temperatures. Those are kind of the takeaways from this. Now we're going to look at a couple of cycles in some detail. This is probably more involved than you guys are really required. Take a look at the homework problems. I think there's some simpler examples there. But we're going to look at what's called a Carnot cycle. And that's at least in part because the Carnot cycle gets used as a reference when we're talking about heat engines and efficiencies. And so let's take a shot at this. Now also, where these heat engines are actually very useful is there are devices called heat pumps, which you may be aware of, that is an alternative to other types of heating systems for homes or buildings of other types. And if you're using a heat pump, what we're going to find is the heat pumps can be extraordinarily efficient. And the heat pump processes are related to the heat engine processes. So let's take a look and see how this works. We could think of this as a Carnot heat pump. And so let's see what we've got here. Carnot cycles operate between two different isotherms. There's a low temperature and there's a high temperature, and that's why we like analyzing the Carnot cycles. What we find with the Carnot cycle is the QH enters the device at a fixed high temperature, and the QL leaves the device at a fixed low temperature. And that means it's very easy to take numbers from a Carnot cycle and plug them into our efficiency formulas that we've developed. So there's an isothermal expansion from A to B. There's an adiabatic expansion from B to C. There's an isothermal compression from C to D. And there's an adiabatic compression from D to A. During the adiabatic processes, there is no Q. There's only work involved in those. So here's how it works. Here is from A to B. That's one of the isotherms. That is at the high temperature. Now there's another isotherm from C to D. That's at the low temperature. For the isotherms, delta E is 0. QH is equal to the absolute value of work. And so the QH here is NR, temperature high temperature, ln VB over VA. Now the way the QLs and the QHs are defined, if you go back and look the last few slides, they're both defined to be positive numbers, and then we put minus signs into the formulas as needed. So QH is going to be an absolute value, as is QL. This is going to be nRTL, ln of VC over VD. Okay, so those are the isotherm values for QH and QL. From B to C is an adiabat. Now for an adiabat, and so is dA, the Q's are 0. And that means that the work is minus the internal energy. And that says that the work will be given by minus 3/2 nR delta T. Now here I'm using their convention. I don't want the minus signs to confuse us. But this is how much work there is during this adiabat, and then how much work there is through dA. Let's go back and take a look at a picture. Where is the work coming into the process, and where is the work leaving? We want the work leaving, that's the work that the engine is providing for us, to be really big. Now, when we are allowing the gas to expand, that's where we're getting a lot of work. So we're getting actually a lot of work along the isotherm, and then we're getting additional work here. When we reset the engine, the reset is done at lower pressures and lower temperatures. The expansion is happening at higher temperatures and higher pressures. And that means that the net work each cycle is equal to the area within the closed loop. So the mantra for this becomes, for a heat engine, is expand at high pressure, that gives you a lot of work output, and then reset at low pressure. Expand at high pressure, compress at low pressure. Expand at high, compress at low. And however much area we can build up within that PV diagram will tell us how much work we're getting out of each cycle. Now, I'm going to bring in those adiabat formulas. I know these are traumatic, but what we're able to do from the adiabats is show that the ratio of volumes volume B to volume C, and volume A to volume D are the same ratio. So what we can say is volume B to C, that ratio of volumes during the adiabatic expansions and compressions, are equal to this ratio. So the volume ratios are the same. Now we can flip those numbers around and say that VB over VA is equal to VC over VD. So it's a little bit of an algebraic trick. Now the efficiency that we want for this is going to be given by 1 minus QL over QH. So I'll take QL over QH. Those were calculated here. That's going to be nRT over nRT high times the logarithm of these volume ratios, and those cancel out. Those go away. And so the nRs go away, the ratios of the volumes cancel out, and it says that for this process, QL over QH equals TL over TH, and that was the condition we said under which the engine is efficient as possible. So now that only works if we have the engine operating where all along that path there is a well-defined temperature and a well-defined pressure at each point. And when you have a rapidly operating engine, these PV diagram analyses become a little bit ideal. When we actually operate the engine, the efficiencies aren't going to be as large as what we have plotted out ideally on these diagrams, but still, that's where we are aspiring to. Okay, so we went through that Carnot cycle. I hope that was reasonably painless. And so for this Carnot cycle, it's very easy to show the ideal efficiency is 1 minus TL over TH. And again, real engines are going to have frictional losses. The best real engines, they're saying, are only 60 to 80% of the ideal Carnot efficiency that we've calculated. Okay, here's a claim. Someone comes in, you're working at the patent office. Albert Einstein worked at a patent office, right? So that's a good thing to put on your resume. You're working at the patent office, somebody brings in an engine and says that the engine, the heat input, or the heat generated, is 9,000 kilojoules at 435 Kelvin, and the output is 4,000 joules at 285. Are you suspicious of these numbers? So you get out your heat engine diagram, and you go, okay, the QH is 9,000, the QL is only 4,000. Wow, I am getting 5,000 joules from 9,000 joules input. I'm getting 5,000 joules of work. That says that the efficiency of this engine this person is proposing has been measured to be 55.6% efficient. That's really extraordinary. Okay, so if you're the patent office, what you're supposed to do is keep an open mind and say, wouldn't that be extraordinary if this is true? And then you say, this has got to be different from any technology we've looked at before, because no heat engine has ever been this efficient. Let's look at the operating temperatures. So using the operating temperatures and the principles of thermodynamics, second law of thermodynamics, we can say that ideally we would expect an efficiency of 34%. So again, you got to keep an open mind. Has this person stumbled onto some kind of a process that we just haven't considered, or is the second law of thermodynamics not as reliable as we thought? Again, it would be extraordinary if this is really the case, but you'd want more evidence. Okay, so you would be skeptical at best and want to see this engine in operation. Let's take a closer look. Can you really tell me how you came up with these numbers? So it is inconsistent with our understanding of heat engines and how nature works in terms of entropy and entropy increases. Now there's a second cycle. I know the Carnot cycle was a lot to go through. There's a cycle called the Otto cycle, and the Otto cycle better represents what goes on in our automobiles. Isn't that a coincidence? The Otto cycle actually applies very well to our automobiles. That's easy to remember. Now, for an automobile engine, it's better represented with a couple of adiabats. So we're going to use these couple of adiabats again, but they're more in line with a constant volume process. So I hope you guys are enjoying. If you're enjoying them, then you're going, yes, another thermodynamic cycle that we can look at. I want to see more. So here's the Otto cycle example. They're telling us, let's go through and look at the Otto cycle. They're telling us what the answer needs to be. They want us to go through and demonstrate that formula represents the efficiency where the ratio of volumes is what we call a compression ratio. Now, if you're into automobile engines, you know that automobile engines a lot of times will be, all the specifications. One of the specifications that comes up is compression ratio. So if I can get the compression ratio to be really high, the ratio of volumes to be really high for this particular thermodynamic cycle, then the inverse of the compression ratio is really, really small, and I can get the efficiencies to be pretty high. Okay? So, and then on the second part of the problem, they say calculate the efficiency using this formula for a ratio of 8, assuming the gases are diatomic. Now, in an automobile engine, let's see, we're getting gasoline, which is like a hydrocarbon. It's like septane and octane and nonane, these different lengths of hydrocarbon molecules. And then we're combining those with oxygen to create water and carbon dioxide. Doesn't sound so diatomic, but anyway, we're going to use the values that we've come up with for diatomic molecules. Okay, I'm very excited about this, I hope, this thermodynamic cycle. So here it is. Here is the Otto cycle. Now remember, these are adiabats, so there's no Q at that time, at that point. But during the constant volume processes, we've got a lot of heat coming in. Oh, these are just pointing to where that happens. So actually the QH is coming in through this cycle and the QL is leaving. This was just an informational arrow, not the direction. I should have drawn it the other way. Now, since these are constant volume processes, notice that VB and VC, they match. And VD and VA match. So I hope you're starting to see the pattern here is with these kind of theoretical, idealized thermodynamic cycles, the way we are able to get through all the algebra here is by recognizing where are the temperatures the same, where are the volumes the same, are the pressures going to match up, and looking for, in the formulas, a way we can start canceling out some of the numbers. So let's see, the heats for each of these processes, for the adiabats, it's 0. Now for the constant volumes, the heats are going to be N times CV times delta T. Now once again, what we're seeing is the QH is coming entirely from B to C. So when I write down QBC, and I write down this formula, that is my QH. And the QL is going to be given by NCV TD minus TA. Now I wrote the temperatures, high temperature to low, because I want to keep these positive. Remember QH and QL, we're going to use those as positive numbers and then put in negative signs as needed. So in our efficiency formula, QL is an amount, QH is an amount, and that minus sign we just put in by hand so we can see the minus sign clearly. There are no hidden minus signs. No hidden minus signs are often a good strategy to avoid errors. So we got the minus sign out there where we can see it. Now in this case, the QH and the QL, formulas look pretty similar again. So when I substitute those in, the Q's from the constant volume processes, I'm getting 1 minus TD minus TA over TC minus TB. So I've got it reduced down to a set of temperatures. Now, it looks like all 4 of those temperatures are distinct. And so we're going to have to move on to the adiabat formula and see if there's a way we could solve this conundrum. Now, the adiabat formula allows us to make a ratio between the two ends of the adiabat. So the temperature at D, temperature at C. I can write the temperature at D divided by the temperature at C in terms of VC over VD. Now, VB is equal to VC, VD is equal to VA. So there's one ratio of volumes. This is the high volume, this is the low volume, this is the expanded volume, this is the compressed volume within the combustion chamber. So this is the piston all the way down, this is the piston pushed all the way towards the valves. Okay, so that says we can take VC over VD and set that equal to VB over VA. So we're using kind of that same ratio of the volumes strategy to, we can replace the, well, in this case we can just replace the VC with VB and VD with VA. When I take temperature A over temperature B, that can also be written in terms of the compression ratio. And look, what that's telling us is TD to TC equals TA to TB. So again, we found a relationship between the different temperatures. So, so let's do this. We can say temperature D is equal to Tc times this ratio of volumes, that comes from the adiabat formula, and Ta is equal to Tb times this very same ratio. So we were able to get the volume ratios. We showed those were the same. So I'm going to substitute this in. I'm going to take this Td, substitute it in, and now that's going to be in terms of Tc. And then I can take the Ta and substitute that in. That's going to be in terms of Tb. So I can take these two temperatures, substitute these two adiabatic formulas in, and that says that Td minus Ta can be replaced with Tc minus Tb times this compression ratio to this power. All right. Again, it's if you enjoy doing kind of traditional algebra. So this actually brings us back to a lot of the algebra that you learn in your algebra classes. How do we manipulate these equations? And it's not just adding and subtracting and multiplying and dividing. It's using a lot of ratios, and it's using expressions to some power. Okay, so for better or worse, that's what we want to be able to do. So I can substitute that in. I can substitute this expression in. All the temperatures now cancel out, and what's left is 1 minus, there it is. It's that compression ratio, VB over VA. I think they had the ratio backwards in the, I want to say they had it backwards. Let's see. I think it's upside down. I think the compression ratio is that volume A is bigger than volume. Oh, they've got it right. Okay. Maybe the formula is flipped. They've got VA over VB. Yeah, I think they have their formula flipped. So they have VA over VB, and what we've got is VB over VA. So the compression ratio is inverted here. And, oh, you know what they probably did? Let me go back and see. Yeah, they put a minus sign in. Okay, I think that's confusing. So anyway, they wrote this. They snuck in a minus sign. They did not follow our agreement of no hidden minus signs. They put 1 minus gamma, but gamma Cp over Cb, that's bigger than 1. That's a minus sign. So I think that's confusing. I would rather follow the approach of no hidden minus signs. And so I'm going to do that. And so I'm going to put it as VB over VA. And I'm going to write it as R over CV. I don't want to write it in terms of gamma. I just want to write it in terms of a 1 minus gamma. The R's and the CV's and the CP's. Now the VA over VB is 8, they told us. They said this is diatomic. For a diatomic gas, the CV would be 5/2 R. So R over CV is 2/5. So this is 1 over 8 to the 2/5 power. And it worked out to be 0.565. So that's a pretty good efficiency. Okay, that's higher than I was expecting. I would like to go in and see what these temperatures need to be. I'd like to see what the operating temperatures would need to be. I mean, first of all, we can see that the pressure ratios, or the volume ratio, sorry, the compression ratio is 8. And so I'm wondering how different, how high the temperatures would need to be in the engine to get an efficiency that high, 56%. Something I'm going to have to go back and do on my own time. Okay? Or if any of you want to stop by during office hours, we can take a look at that together. All right. Now let's talk a little bit about heat pumps. Heat pumps are heating or cooling devices. So they provide both heating and they provide cooling. And what a heat pump or a refrigerator or an air conditioner does is it uses a mechanical system. It uses a compressor. So you plug in a refrigerator, and the refrigerator operates a compressor, and that creates a mechanism where we can actually transfer heat out of the refrigerator. Now that's backwards, right? The inside of the refrigerator is cold. The outside of the refrigerator is warm. Shouldn't heat be going in the other direction is what we have to ask ourselves. And so the next item we want to look at is a heat pump. And let's go ahead and get started with that. We'll probably stop and take a break along the way here. So you can see it's the very same diagram we had before. This is a heat pump. Here is a refrigerator. So the way the heat pump is going to work is this. You take the power cord and you plug it in. And the refrigerator works. It's kind of amazing. Okay, the detailed workings is that when you plug it in, it operates a compressor. So what I've got here is, see this compressor operating here with this piston? There's a couple valves here, and so the piston moves back and forth. That's being operated by an electric motor. That's the energy input. So I got to put some energy into this. What it does is it takes a coolant material which we have filled inside this set of pipes. So here's a set of pipes that carry the coolant and they cycle through. Now the compressor is being used to both pump the coolant in this direction, and halfway through there is what's called an expansion valve. And the expansion valve turns out to be just a small, tiny opening that allows the coolant to come out from this half of the piping and enter the other half. Now, because there's a tiny opening here and this compressor is going, all crazy, this side with the coolant goes to high pressure and high temperature. So this side is at high temperature, high pressure. On the other half of the piping, the other half past the expansion valve, as the coolant comes through, this is called a throttling process, where you take a small opening and you let this gas come through. It turns out the molecules as they come through lose a lot of energy. Okay? They can even undergo a phase change into vapor. Now if they undergo a phase change into vapor, now this says it's high pressure vapor, this is low pressure vapor, but we're working with some kind of a fluid. In either case, what happens is that the temperature of the gas molecules, or the coolant, in the second portion have now dropped to an extraordinarily low temperature. Okay, so it has to do with the potential energy, the attractive forces between the molecules in the coolant. So when we go through this high pressure, high temperature side through the expansion valve, we create a low pressure, low temperature side. So the coolant on this set of pipes is really, really low temperature. The coolant on this side is at a really, really high temperature. Now it's a refrigerator. What should we do with the really low temperature coolant? Well, let's run these pipes through the interior of the refrigerator. All we have to do is set this up in a way where the temperature of the coolant is lower than the temperature of the freezer or the refrigerator. And we can do that. So we can find coolants that as they go through the expansion valve end up losing a lot of their internal energy. They go to really low temperatures, and that draws thermal energy from inside the refrigerator. So these coils run through the interior, and then they return to the compressor. Now on this side, this is the high pressure region, high temperature. Those temperatures are much higher than the ambient temperature of the room. And that means that the heat gets radiated away. So it's called a heat pump because effectively what we've done is we've taken heat away from the interior by running this cold coolant through that. And then on the other side, the coolant is hot. and that radiates heat into the room. Okay, and I've become a real heat pump advocate, not because I just recently got a refrigerator, but I recently switched over from a natural gas furnace to a heat pump in order to heat my home. And it's the same principles are at work. We have a large compressor outside the house that's operating. It's really quite quiet, and it's super efficient. And it's got a set of coolant pipes that run into the house. And to heat up the house, what we do is we run the coolant through the set of pipes, going through what's called an air handler, and then fans blow air past that handler, and then that heats up the house. Now, while we're heating the house, we can go outside and look at the fan blowing through the condenser, and that turns out to be cold. So you can actually, when you're heating the house inside, you're going, where is all this heat coming from? Well, it's being pumped from the outside, and the fan operating at the compressor outside is blowing this air, and the air is coming out really cold, colder than the ambient air. So you're taking heat from the air outside, even though it's at a lower temperature. The coolant has been dropped below that temperature, and that enables it to draw thermal energy in. And then on the other side of the compressor, the work is going in to compress the coolant, and we end up sending that inside the house. So effectively, we're pumping heat. Now, the nice thing about the heat pumps is they can be used to heat or cool. So the heat pump that we have can reverse. There's a valve where if you want to cool it, it switches the direction that the coolant is going. So now the high temperature coolant runs through the outside of the house, and the low temperature coolant runs through the inside. And so that cools the air on the inside, and when you're cooling the air on the inside and you go outside and stand in front of the fan on the compressor, it's hot. And so you go, there it is, it's pumping that heat. Heat's leaving the inside of the house, and here it comes. I can feel it coming outside the house. So let's see, maybe that's a good place to stop, and we'll come back and talk more about heat pumps. Yeah, let's do that. Let's stop right there, and we'll come back and continue. If you guys have questions, let me know.